Now we're missing 2 other students. So.
Yeah, I'm waiting for them for 1 more minute. It's already 1:15.
Okay.
Last time, like here, right? I talked about the complexity class. So as far as I remember, the end, the last slide of the last session, apart from the lab we had, was the complexity of CSP and 3-SAT, and I explained what are actually SAT are, what are CNF, what are DNF in general, and 3-SAT is a hard problem, and 2-SAT is a problem that actually we know how to solve with polynomial. And I'm not going through that again, but I started with the fact that CSP as SAT. So constraint satisfaction problem is a problem assigning values to variables such that all constraints are satisfied. And SAT was the same thing. SAT also is a CSP where the variables are Boolean variables and the value could be true and false. And the problem is to assign the first value to all those variables such that all constraints are satisfied if those constraints are represented as CNF. And what was CNF? CNF was the conjunctive normal forms. And this is basically conjunction of the clauses where each clause has only literal, where they're in relation or they're on disjunctive relation upon each other. So, and in CNF, conjunctive normal form, we cannot have a negation behind a clause. Negation could only be part of literal. And literal is a variable, for example, Q, or it's negated. So when I'm talking about literal, I'm talking about either of these two cases. And the clause is this, and this is disjunction, and this is conjunction. And 3-SAT, which is a hard problem to solve, it's an empty complete problem, is the problem of when all the clauses are, where all the clauses have 3 literals. For example, in this case, 3, 3, 3, and this is called the 3-CNF. And then the problem of finding the model for these 3-CNF called 3-SAT, which is a difficult problem, is empty complete, meaning that we don't know yet polynomial time algorithm to find the model to this problem. Whereas 2-SAT is simple, is in class P. So this is a brief review of the previous section. So you need to know this terminology in order to follow the rest of the SAT lectures. So it's very useful that actually we represent CSP as SAT. Why is that? Because the SAT solver are very efficient. SAT solver can deal with millions of variables. Nowadays, my usual example is a lot of verification tasks in your Linux or operating system actually run a lot of SAT solver, and they have millions of 1 million of variables, for example, or thousands of variables. So it's very useful that we actually represent CSP as SAT. And another reason, apart from having the reason that we can have a very efficient solver for solving SAT is SAT has a normal form. So the structure can help us to do a lot of efficient propagation technique. So in CSP, the constraints could be anything, could be any language. We didn't define any particular language to describe math coloring, but in this case, we have a concrete language that is a language of disjunction between the clauses. So this compact form, or as it's called, normal form, help us to do a lot of efficient reasoning like search and propagation. So how we could convert a CSP to a SAT? So every CSP can be translated. This is very important. Every CSP can be translated to SAT. And if a CSP has n variable, and each variable has d number of values, domain size is d, we have d SAT variable, meaning that each clause has d literals, and in general, a SAT problem has n times d variables. Also in CSP, the solution to a CSP is assignment from value to variable, meaning that at the end of the CSP, when we find a solution, each variable has one value. Therefore, we have to introduce clauses that represent each variable has only one values. And for doing so, we have to add extra clauses. How this is going to work, I make a concrete example, you will see immediately why it's the case. But for now, is the number of clauses that we have to add is n times a combination of 2 out of d plus 1. So, but remember this, I'm going to explain it later by example why this is the case. And CSP is represented by a series of mutual exclusion. For example, we say that two regions in Australia map cannot have the same color. So we represent this as this conjunction of clauses, and the number of clauses we have to add per variable is per constraint is e times combination of 2 out of d clauses. And if you put n like 10 and d like 3 and compute these numbers, it actually becomes a large number of variables and constraints and clauses per very simple example. But despite of the size, we can still solve a SAT problem, which is equivalent of CSP problem, very efficiently. And this is a promise I make, but I will tell you the propagation technique that we're going to use for the SAT, and you will see immediately why having this kind of form help us to have this efficient algorithm. But first, have an example. I go through this example in board. Let's see. So our CSP is, this is a constraint graph, and this instance of constraint satisfaction problem has 4 variables A, B, C, D, and the domain of each variable are red, green, blue. Domain are equal for all variables in this problem, and constraint, we have 5 constraints that are A has to be should not be equal to B, and A should not be equal to C, and C and B should be different, and so on. It's easy. The goal of this example is we represent this CSP as a conjunctive normal form, which was conjunction over clauses, each clause was disjunctive over disjunction of literals. First, let's represent each variable. So per variable, like a variable in CSP A, we should represent the variable of A. Sorry, I did not do A. X of variable A being R, being red. And another variable, the situation, the state that X for variable A would be green. and x variable a would be true. So basically this is a Boolean variable. What does it mean? This can be true or false. If xar would be true, meaning that the variable a in CSP has red as its domain, right? And if a green, what does it mean? If it's true, meaning that the variable a in CSP has a green color. And it's the same for xab, which means that variable a has a blue color. We have to do the same thing for variable c, and these are Boolean variable, right? We have to do the same thing, for example, for c, I'm not going to write all of them. So we have 4 variables, each of which has 3 domains, so 4 times 3, 12 Boolean variables we have. This is similar as this. Well, we know that n times d is quite intuitive actually. So, because at the end of the story we want to predicate over Boolean variable. We want to assign that which variable has which color, but we have to represent it in Boolean variable. It's not the case that it's like a CSV variable can have red, green, blue, and we write red. We have to say the domain, we have to represent variables such that the domain could be true and false. As I said before, so the solution to CSV is when we have one value per variable, meaning that A only could be red or green or blue. It cannot be red and green. So just let's write what I just said. So variable A, which now the language we have to work with is only Boolean variable. The variable A in CSP only have to be red or green or blue. But it cannot be both green and red at the same time. And it cannot be red and blue at the same time. These are A.
That's CNF, is it?
Yes. Wait a second. And I get there. And it cannot be X. A cannot be red and cannot be green, right? I'm just saying what it cannot be in CSV, but in the Boolean forms with the Boolean variable. And also A cannot be at the same time blue and green. So far so good, right? Everyone with me. But as he pointed out, if this is not a normal form, I just told you before getting to this, we cannot have negation behind the clauses, right? We cannot have that because this is not a conjunctive normal form. And I told you it's extremely efficient representation that we have our formula in conjunctive normal form, because further on we're gonna really use this representation. So what is very easy, how we transform this to CNF. We have this Morgan law, which this remain the same, and this becomes negation X AR or negation of X B, and negation of X or negation of X A green, and we just basically bring this negation into each literal in the class. And this is a normal form. And all these 4 clauses only is for A. We have to do the same thing for B and D and C. Basically, there are 4 variables, each of which meets the 4 clauses. Basically, we have 4, 16 new clauses. It is clear. I don't write the same formula for B, D, and C. And this is on the slide, by the way, so you don't need to write. If you want to write, it's fine, but they are already in a slide. So this is basically what I wrote in the board, but here is directly written as CNF. I thought it more intuitive if I write it first as negation of clauses and then in the CNF form. And this actually is n times 2 out of D, which D is here is 3, and plus 1 comes from here actually. So it's 3 plus 4, and n is 4 in this variable, therefore it's 16. So now you know that why this comes from 1. This is for the case that each variable has to have one of this value, and these are for mutual exclusion. And now we have to write the constraint. What would the constraint look like? Actually, now it's simple. We should write, for example, A and B should not be read at the same time. How we write this? X A, variable A cannot be read. This at the same time cannot be true, right? XAR, meaning that the variable A in CSV cannot be read at the same time a variable B has read as its value header. So what happened then? We know it from here, from the Morgan law. We are ready to write like not. Oh, sorry. R or not. And we have to write this for all the combination of the constraint and the assignment of value per variable, which is represented in Boolean variable here. So, and for example, not X A B blue or not X B blue. Okay, it becomes a bit messy. I'm not going to write all of the cases, but you get the idea of why it should be the case. And per constraint, so in general, since we have 5 constraints, so each of which, how we calculate this? I gotta work this here. 3 multiplied here we have, and the variable is E, which is we have 5, 1, and 2 E, and is 3. And the two combination of out of D is basically represents the mutual exclusion that we can have here. So all the combination of all the selection of mutual exclusive assignment of value to variable, which represents the Boolean variable here. So in this example, you get some idea of how we can represent the CSV with all these different constraints to SAT, which is very simple. Just you have to first represent your Boolean variable and you write what you say. Basically, it's nothing very complicated.
How would you represent the constraint that that's not equals, but an equals? That would be a lot more.
A lot more.
Yeah. Okay.
Yeah.
You have to basically say that every combination they can't be, rather than every combination.
I guess in next slide I'm going to explain that naive transformation of CSV to SAT could make really a formula much larger.
Yeah.
There are a specific way to represent Boolean satisfiability to the CNF, but in the first place you have to represent that CSV to a what is called, to a random SAT, and then we have a very efficient way of representing that SAT to a CNF. So, you know,
Okay.
so it's just normal formula, but the premise is if we have it in CNF form, we can really solve it efficiently with respect to CSP. This is not in the scope of the class. CSP solver nowadays also is very efficient, and the reason they are efficient is because of something like notion of global constraint. And since people really focus on problem-specific constraint propagation, they also become very efficient. So it's not generally true that you have to always convert every CSP to SAT. I was in a PhD school in 2015 in Lille. It was a constraint school, and there was 3 communities there, were CSP, SAT, and ASP, ancestor programming. And these communities are not the same community. The people working on SAT does not necessarily work on CSP, and the difference are people become very specialized on defining the propagation rules, defining what kind of constraints are efficient to represent, how we can represent, and things like that. And if you ask a guru in CSP, it's not the case that he or she would tell you, okay, you have to translate your CSP problem to a SAT or the other way around. Of course, people want to, you know, what is called, stick to its own expertise. But in reality, SAT solver are very efficient just because the language are so similar. So you don't need to learn a lot of language-specific CSP. That's my neutral opinion, because I did my PhD in CSP actually, but I think SAT still are, off-the-shelf solver are very, very efficient. And just because of the language they have. They are actually CSP language, if you are into these things. Minizing, I can work it here. It has a CSP, it's extremely efficient CSP-based language, which is called constraint programming. It's developed over years in University of Australia. I don't know which university in Australia, but big university in Australia. So in case you want to really solve your CSP problem efficiently, this is the language that I personally recommend. Anyway, back to this, but all those stuff that I said was out of scope of the class for your general knowledge in case you're interested. So, well, in this slide it just said that what I said several times. So many interesting problems can be reduced as SAT. Task planning and scheduling, you will see, I guess, in your automated planning and scheduling course at the end of this academic year. Graph planning, off-the-shelf solver, use actually SAT solver. You don't see SAT, but it's off-the-shelf solver. But the reasoning behind that is basically based on SAT. You remember the planning problem I told you in the introduction course? It was Hal had a plan to kill Frank and Dave. So I represented a sort of planning problem to you in a very informal way. So in order to find a path, a set of action that Hal can kill Frank or Dave, is the solution to a planning problem, and how those solutions could be found. Actually, we can translate those action theory to SAT, and SAT could immediately find such solution. So that's why I'm saying that the planning and scheduling could be used SAT. And sorry for the it's still wrong. And I have one more polynomial spelling error in this slide. And the reduction could be polynomial, and model leads to solution of original problem, meaning that if you solve the problem, if you find a model in this formula, is like solving DCSP originally. These are equivalent. And the SAT solver are known to be workhorses of AI. As I said, they can solve problems with really large number of variables. But the problem is, if you naively convert our SAT to CNF, can be really disastrous. Size of formula can grow exponentially, and that's not what we want. Because, for example, some formula like this, which is not CNF as you see, because this is this junction between the clauses, and the clauses are conjunction, and it's actually this particular formula is DNF. But anyway, if you naively transform this to CNF, the result of transformation would give us 2 to the power of n clauses. And basically, size of the problem would grow exponentially. I'm not going to read this example because this is just an example of how you can be naive in transformation of a SAT formula to CNF. But the thing is, what we are actually doing that, why we are transforming formula to CNF, because we want to find a model, or even we are not necessarily interested to find a model, we want to just see the given formula is satisfiable or not. There is a certain process in your Linux, and we want to say that, okay, this should I tell the user that's going to be an error or not? Basically, we want to just give an answer to the satisfiability problem. In this case, so we are not really interested to transform the formula to an exact equivalent, so rather we can introduce new variables, because all we are interested in to answer the question of satisfiability. Or perhaps we're interested in the model, but the thing is, the important thing is, we may not preserve exact formula. What we are interested in is to preserve satisfiability if we transform one formula to another formula. The concept which is very important here is self-preserving transformation. And what does this mean? So we transfer formula phi to phi prime, and phi is sat, means phi is satisfiable if and only if phi prime is sat. And this is sat, this means equally satisfiable, which means that if I have a formula in CNF transforming to another formula, so if the original formula is satisfiable, and if I use the self-preserving transformation, the result has to be satisfiable. Otherwise, this transformation is not self-preserving. So self-preserving transformation keeps the most important characteristic of the formula itself, that is satisfiability. And again, another important property is if I transfer phi to phi prime, and size of phi prime has to be linearly bigger than phi. If it's not the case, if it's exponentially bigger, this is not self-preserving transformation. And this second property basically is the same as transformation, introduce only linear number of new variables. And as you will see in the example which I'm going through, the idea behind self-preserving transformation is adding new variable to the original SAT formula in order to facilitate the transformation. Because as I said, we don't want to necessarily keep the original formula, we only want another formula which is equivalently satisfiable, because we want to answer the question of whether this formula is satisfiable or not. And the last important property is the model we find for phi is projection of the model of phi prime or an original variable. So phi prime is bigger than phi because I told you we introduced new variables for this transformation. And if you project those variables that were in phi on phi, that model still has to be true, the model defined for phi prime. That's the definition of projection. Okay, how are we gonna do that and do this transformation? I go to an example again on the board that you will see how this is going to work. Should I delete? I mean, no one needs this, right? It was already on slide. So the formula that we have is P or Q and R and S. So I went through this yesterday with myself just to make sure that I know it. It's really interesting to do these things by hand because it's very error prone. It's much easier to write in a program because then you wouldn't make mistakes. But the idea behind this, the idea behind transforming this formula to a SAT formula, which is basically CNF, and has these properties, is to introduce new variable for subformula. And what is the subformula? This is one subformula, this is one, and this is one. So he says P1, which is a new variable, is equivalent of P. Let's write exactly how I wrote it in the slide. That was R, right? And I just say that this is, sorry.
Q and not?
Not R.
Oh.
Thank you. So what I did that, I'm saying that the P1 is equivalent of this. And P2 is equivalent of P1, or that was P1, right? Or P. And P3 is equivalent of this is P2, right? P2 and S. I had exactly the same thing in the slide, so just in case you don't want to write. I put parentheses here, it's easier for me. And P3 itself, because all of this has to be true. So let's transfer the first subformula to CNF. So from it was logical implication. Yeah, here it is. Logical equivalence. From the logical equivalence, we know that P is equivalent to Q is P implies Q and Q implies P. Therefore, we can write this part is P1 implies Q and not R, and Q and not R implies P1. We know this from the logical equivalence rule. So we know from implication rules, P implies Q is not P or Q, and you will see why is that, right? If it's P true, therefore Q has to be true. If is not P true, which is not P, therefore Q cannot be true, so we don't write it. So this is not P or Q. So we translate, put the parentheses, P1 implies to Q and not R to the following. either is not P1 or P1 not R. This could be, wait a second. Division 4. So, not sure this is correct. Yeah. And this one it becomes not Q and not R or P1. Am I correct so far? It's really easy to make mistake in this thing. Because on the slide I have only the final result. I don't go through the exact details in the slide. So from this logical equivalence, P1 implies this one, and this implies P1. We know from multiplication rule this is not P1, or this is correct, and not Q and not R, or P1. Okay, so
You're missing a parenthesis, maybe?
Sorry?
Maybe missing a parenthesis.
You mean, okay, I can put parentheses here. That would be
Yes.
correct.
Yeah, there's one more opening than a closing. The first one on the line is not closed anymore.
Oh, okay, I can put it here too. Right. This is for a while. Okay. So still we are not in the CNF for many reasons, and at least one obvious reason, well, there's more than one reason. There are these negation behind the clauses, and that's not allowed in CNF. And let's start with this one on the left. So this is also not CNF because we have this is not a clause should look like. We have inside the clause we should only have literal. So what we can do, we can use this rule, associated law, in order to basically associate this disjunction over the parentheses. That could be not P1 or Q, and not P1 or not R, which is, this is CNF, right? This is a conjunction between two clauses, each of which has a disjunctive between the literal. And this one is a moral law. If you can have not Q or R, then tell parentheses doesn't matter because it's the same if all of them are or, and not P1. So all of this I wrote is only for this first one. And here we have CNF, right? We have and these are or between each literal. I'm not going through all the three ones. You can go at home. But basically this is the idea. I add new variable, and through kind of manipulation of certain laws, which I listed here, we can achieve the CNF. Okay, this is the end result of the CNF formula. If you go through this at home, compare it with this. I made many mistakes, by the way, but I don't think so. I went through it once, but this is very mistake and error prone, and do it by hand. It's much easier to write it in a program. Anyway, so you get the idea, and this is basically a very basic example of self-preserving transformation. What's the time? Okay, it's actually a good time to take a break. And be back 10 past 2 because after this slide I have a propagation rule, so it's good to make a break now, not to go to propagation.
Why?
Go ahead.